All right, welcome everyone. So the goal for today will be to just kind of continue reviewing questions from the homework and from the practice test. Remember, your first exam will be next Tuesday. It will be very similar to the practice and similar to questions from the homework.
Try to catch you in the radio.
1 second.
Boom, boom, boom.
Okay. Oh, you don't need to turn in the practice test. However, so Lily asked you a question, should you turn in the practice test? You don't need to turn that in, but you are welcome to turn it in if you want me to take a look at your work and just check it out. So if you do turn it in, I can give you some feedback on it, but it's not required at all.
Are there answers anywhere for the practice test?
No, I won't post the answers, but I don't have a copy of them, but you can ask under the comments. You guys can discuss, and I'll reply to comments underneath that practice test chat. So that's a good place to ask if you're not sure about any of them.
For the test, are we going to be graded just on whether or not our answer is correct, or will we also need to have well-organized work?
Yeah, I would like to see your work. It doesn't need to be in great detail. Like I think the detail that I usually use to kind of explain, okay, I'm doing like 5 choose 2 here, minus 5, and just kind of explain. You can just write that down, or try to explain your reasoning. You don't have to go into too great of a detail. Let me see. If you want to get feedback on the practice test, I see I made it a material. I can repost it as a assignment, so that way you can ask for some feedback. But the best thing, if you want to just check your answers, I encourage you to please just chat. You guys can leave comments, and I can get back to your comments on the actual practice test. I think that's a good way to ask to get feedback. I can turn it into a actual assignment so that you can submit your work. But I prefer just if you ask a question, this way everybody else will see as well. Okay, let's do this one. This was number 29, and we kind of left off last time. Here, this combines two ideas, and one of the ideas we haven't quite seen before. So the idea is you don't want bio, history, or programming to be together at all. So let's think about the complement. So let's use the idea of the complement. So how many ways are there to have either biohistory, programming, or history, programming, and bio separate, or what is it? Bio, programming, and then history separate, or bio, programming, and history. So if we can count the number of ways we can have all of these scenarios happening, we can figure out what we need to subtract from 8 factorial. any of these scenarios is totally okay. So how can we calculate it? It's a little bit tricky to do biohistory together, but separate from programming, right? You'd have to kind of make a super letter and then make sure it doesn't touch another letter. So that could be a little bit, seems a little bit intensive. So what we can do instead is we can overcount. So what if we say instead of counting these things, just count count biohistory and just ignore programming. Because the case where biohistory and programming, biohistory are together, and programming is also next to one of them, that actually falls into the case where all of them are together. So what we're going to do is we're going to overcount, and then we're going to adjust by all three of them being together. So how many ways are there for bio and history to be together? There's 8 books.
7 factorial.
7 factorial. And then what else do we want to include? Because we make one super letter with a B and H.
Over 2 factorial? No.
Not over, but 1, 2.
Times 2.
Times 2 factorial, because we want to count that it could be history or bio. So 1, 2, 3, 4, 5, 6, 7, 8. Looking at this. So this gives us 7 factorial times 2. However, the thing that we don't want to include here is we want to make sure that we remember to take away the cases where all 3 of them were together. So now take away, to get, let me just kind of write here. So first, and then subtract biohistory and physics. That would give you just the cases where biohistory are together, but you're taking away the cases where biohistory are together and physics is also next to them. And how many ways are there to do biohistory and physics? This is, we're going to subtract, this time instead of 7 factorial times 2 factorial, what would it be? Nice. Excellent. So it would just be 6 factorial because we have a super letter now with 3 letters. And that gives us overall 6 things to choose to rearrange. But then the inside one, we got to have 3 factorial ways to do it. And so here, so the first group, the first formula that you end up with is 7 factorial times 2, but you adjust for the fact that you don't want to include the case where all 3 of them are there. Okay. So what we can do next is for history and physics together, but not bio, we can just triple. We do the same exact thing, right? And the same for bio and programming, but not history, you can do the same thing again. So for each of the cases that we have, if we want to count either two of the books together and one of them not together, one of them separate, you could just do this 3 times. But then, these are the three pairs, uh, 3 cases, this is 3 cases, these are 3 cases, 3 cases of books in a pair, and one separate. And then the last case that we want to include is just putting back in, so all these cases don't include the case where the 3 of them are together. So you just want to make sure you count that back in. So you have this. So this is the complement of what we want. So our final answer will be 8 factorial minus this whole thing. And if you factor this, this whole thing out, so our answer would be 8 factorial minus, and then in parentheses, 3 times 7 factorial times 2. And then I'm going to look at this as a like term, look at these guys as like terms. So if I subtract 3, but then add 1, it's like just subtracting 2. So I'm going to do minus 2, and then in parentheses, 6 factorial, 8 factorial. Okay. And let's see, this might not be too bad. To simplify, maybe you can observe that maybe we could save ourselves a little bit of time to calculate this. This would be 8 times 7. Everything has a 6 factorial in it. So this is just a calculation trick. So this would be 56, which is 7 times 8, times 6 factorial, minus 3, 2, and then 7 is 6. So 42 times 6 factorial. Minus 2 times minus 12. 2 times 6 minus 12, 6 factorial. Grouping these terms together, 42 minus 12 is negative 54, and then 56, so combining like terms, you just get left with 4 times 6 factorial. So this is, you could have just also plugged it all into a calculator. I'm not going to expect this type of calculation on the test, but let's just take a look. 4 times 6 factorial, and it got 2880, which I hope is the correct answer.
I don't think so.
Hmm.
Options on the
Yeah, what did the answer come out to be?
You forgot to distribute the negative sign.
Oh, thank you. Yes, it's a plus. Okay, so then that would be, oh no, that would be a lot bigger. That would be, thanks,
The
man.
answer is, yeah, a lot bigger than that.
So that would be what? 26 times 6 factorial? Am I doing that right? Negative 42 plus 12 is negative 30. Yes, so that would be 26. And does that come out better? 26 times 6 factorial. 18,720?
No, it should be, the answer is 14,400.
14,400. Okay. So I have an idea what went wrong here. It might be an interpretation, but does anyone want to suggest kind of another approach or see an error in any of this? Let me just try something really quick here. Minus 6 factorial. Hmm. Yeah, does anyone have any thoughts here? I'm not sure.
I can explain what I did.
Yeah, go ahead.
So I started out with 8 factorial because that was how many books there were originally.
Yep.
And then I looked at the history, programming, and biology and used 3 factorial for each of those. And then multiplied 3 factorial times 3 factorial times 3 factorial times 5 factorial. And then subtracted 8 factorial from the product of that. And so that would be 40,320 minus 25,000.
Can you tell me, so you did 3 factorial?
So it was 8 factorial minus 3 factorial times 3 factorial times 3 factorial times times 5 factorial. And then, so that would be 40,320 minus 25,920, which got me 14,400.
Very good. Oh, I see. Yes. 1 second. Wait. 3 factorial. For some reason, it's 8. So you did 8. So this becomes actually a 6. So this is the same thing as 8 factorial minus 3 factorial times 6 factorial?
Yeah.
That's correct?
I think so. Hold on.
But
Yeah.
For some reason, Google's not giving me the right value for that. I don't know why. Huh. But that checks out to be the right number?
Yeah, when I did it, I got the right number.
Okay. I like that. Let me see. Google is telling me 36,000. But the answer is 14,000? And you got 14,000?
Yeah, 14,500. But
Does that make me wonder?
so I did. So 3 factorial. So there's 3 factorials.
Oh, there's 3 factorials.
Yeah.
Oh, I see. There's another 3 factorial here.
Yeah, because there's three different books that shouldn't be next to each other.
So there's another one here. So how did you come up with the 3 factorial, and then 5 factorial?
Well, I did this a while ago, so I can't really remember my exact thought process, but basically because of the, so I know the 5 factorial came because like 8 minus 3, which is the amount of books that shouldn't be next to each other.
Okay.
So like 5 is the remaining amount of books.
Mhm.
And then I think so because there's 3 different kind of books. So there's history, programming, and biology. So like that's 3. And then for each of those, it's like 3 factorial. I don't know if that makes sense, but that's kind of what I have written down.
Uh, yeah, that definitely makes some sense. I'm not sure. I have to think a little bit about it. But it's a nice formula. I don't see the exact justification there. Hmm. Oh, wait a second. Wait, 12 to what's interesting is this is 26. Well, yeah. If anyone has a good explanation for that formula, um, yeah, definitely welcome to share it. I have to think about this a little bit. In particular, also, I'm curious where my logic went wrong originally.
Wouldn't 8 factorial be the number of ways you could arrange the total system? And then 5 factorial would be the number of ways you could arrange the 3 things, right? So then each 3 factorial would then have to be how you could separate them. No, never mind. I don't understand it. I thought I did for half a second.
Yeah, I could see 5 factorial as like the way to arrange the other missing books. But then why do we have 3 factorial, 3 factorial, 3 factorial? Hmm.
I can share my way if you want. I know I definitely got the right answer.
Yeah, go for it.
Um, so I also started with 8 factorial, and subtracted from that. I also did 3 times 7 factorial, 2 factorial,
Okay.
but I didn't subtract the 6 factorial, 3 factorial, the overlap. So if I did 8 factorial minus 3 times 7 factorial, 2 factorial, and then I added back 6 factorial, 3 factorial.
Oh,
And
I
I did
see.
that
Yeah.
because, like, the way you described it last time, you described it with the what's it called? I forgot what the chart name is, but like this.
Right. Yes.
So if each one of the circles is 7 factorial, 2 factorial,
Uh-huh.
then this middle section, where is it? Where's the draw option? This middle section right here, that's going to be 6 factorial, 3 factorial. So that's the overlap. So I added that back, and I got 14,400.
Very good. So let's see. Let me think. Yeah, so I think I'm just somehow adding and subtracting things incorrectly that are not overlap, somehow miscounting overlap. Yeah.
I'm pretty sure it's because you put the 2 in front of the 6 and 3 factorial.
Okay.
It shouldn't be times like 2 of the 6 and 3 factorial, just 1.
Just
And
one of them.
Yeah, I put that in a calculator without the 2, and it's 14,400.
Oh, okay. So then, oh.
Yeah, that's what I did. That equation that you just made right there, that's exactly what I had.
Okay, so I see the error here. Yes. So the problem is when I do this 3 times, um, I need to include, let me see, somehow I need to make sure that it's a 2 here. I thought there's a 2 here which would cancel it out. Why does there need to be a 2 there? Um, yeah, it has to do with that picture that Lach is drawing. If you add the 3 circles, yeah, if you add the 3 circles together, or you subtract that middle portion 3 times to get the overall overlap, you want to add it back in 2 times. I think that's the idea. Okay. This would be just the 6. Uh, this is also a nice idea. Okay, so yeah, this one I'm going to think more carefully about where I miscounted a little bit. But thank you guys for stepping up and helping me find my mistake. I am curious if there's an easier way to see this last equation. That's really nice as well. So that could be something worth thinking about. And I hope you also see that with these types of problems, it's they are not always as clear. You have to spend some time thinking about them, and it's okay to make mistakes on them. And it's a fun process. So there won't be one like this where it's like inclusion exclusion with 3 overlapping possibilities, and you got to kind of readjust it. But there won't be something like this on the test. So don't worry about that. But this is definitely worthwhile problem to think about. And maybe I'll do a more careful write-up to do a better job of explaining. Okay, let's move on to another question. Number 30, yes. Yeah, Alex, the question will be very similar to the practice test. There might be like a question or two that's different, but it'll be similar to the homework. But essentially, it'll be like the practice test, but with different numbers.
Cool, thank you.
Mm-hmm.
I had a question about number 40.
Yeah.
It says it asks us to find the constant in an expansion.
Uh-huh.
And what I assumed was that would be x to the power of 0, y to the power of 6.
So constant would just be something with no x's and y's.
Yeah, but both of the terms in the expansion have an x in it. Does that mean the easiest way to do this is to expand the whole thing out, or is there a quicker way to do it?
Okay, so let me do, let's do number 40. So this one is 2x squared minus 1 over x to the 6. And say, find the constant term. So this would be exactly, let me clear the annotation. So this constant term is just a term with no x's. So is the coefficient of x to the 0. So if you're expanding this, and we're thinking again to use the binomial theorem here, where this is like a, and this term is like b. This is a, b. What you realize is that every term that you get in the expansion, you could just expand it all out and plug it in and then be careful with your exponents and minus signs. But you can also try to just do it directly. What you find out is that your terms will look like 6 choose k times 2x squared to the 6 minus k times negative 1 over x to the k. And hit yes if you're comfortable with the formula that I just wrote down. Another approach is to also just start writing it out. So some people aren't comfortable, a few people were. Let me kind of, before I jump into the way of doing it with the formula, let's just start by reminding ourselves what the pattern would be to expand this. So the first term that we have would be a to the 6th. So we would have 2x squared to the 6th power. Then the next term would be plus 6 choose 1, 2x squared to the 5th times negative 1 over x to the 1st power. And then plus 6 choose 2 times 2x squared to the 4th times negative 1 over x squared. And it's going to keep going all the way until you get to negative 1 over x to the 6th. So give me a thumbs up or yes if you're comfortable with that expansion. And we're just plugging in these, somewhat complicated, like a negative exponent, like a 1 over x and 2x squared, into the binomial expansion for a plus b to the 6th. Okay, and now you really have to make sure you're comfortable with doing exponents of exponents. So, for example, over here, you'll get 2 to the 6th, which is, that's a pretty big number. That's 64. So what you'll get is 64 x to the 12th plus 6 times 32, which is going to be big. But now it gets interesting, because you have x to the 10th, but you're multiplying by minus 1 over x. So that will become an x to the 9th. The next one will be 6 choose 2, and that's going to be what? 6 choose 2 is 15. So 15, 2 to the 4th is 16, times x to the 8th, but this time it's over 1 over x squared, the minus sign goes away. And what you notice that's kind of neat is that the powers of x are no longer just stepping down by 1. The actual powers of x, like whatever these numbers are, I'm just going to do dot, dot, dot. This will get you to 64 x to the 12th plus, well, not plus, it's going to be a minus sign, minus 192 x to the 9th plus, I want to say 230.
Wait, how did you get 192 x to the 9th?
6. Yeah, just 6 times 32. Is that right? Yeah. 6 times 32. And then 15 times 16 is 240?
Yep.
Cool. And then the power is x to the 6th. And this will keep going all the way until we get 1 over x to the 6th. So, go ahead.
Are we trying to find the, what are they called each step? Are we trying to find the step where the x's cancel each other out?
Exactly. This is kind of a really long way to do it. Like if you wrote everything out, you could do it this way and figure out which one's the constant number, but that would take a lot of work. Like it would just be very tedious and easy to make a mistake. But are you guys seeing what's kind of interesting about this one is that the two terms, one of them has like more than one x, and the other one is a reciprocal of x, like a reciprocal power of x. And so when you're taking different powers of them and multiplying them, they're doing this cool thing where they're canceling each other out. So it gives you this kind of unusual pattern a little bit. But we don't need to do the whole equation to solve the problem. Like Alex suggested, we could just focus on how could we figure out which term would be the one where there's no more x's. In particular, now that I've walked through the kind of writing a few of them out, do you guys feel comfortable with the with this expression? This is just a general expression of like for different terms in the expansion. And like to do the full expansion, you would do different values of k. Okay, so I'm just gonna copy here. And you actually don't need to do anything too fancy here. The one that you'll be given, like similar to this, you can just do by, you can essentially just do it by guess and check or inspection. So our goal is to find a k to make x to the 0. So here's a really simple question. Think of two quantities that add up to 6. So two numbers that add up to 6, just like we have here and here. You know, these two always add up to 6 and 0. Where these two numbers that add up to 6, one of them you're going to raise x squared to, and the other one you're going to raise 1 over x to. And then when you multiply them through, they vanish. So if you want to get fancy, what you could do is actually look at the power of x algebraically, but you can also just do it by inspection. If you need to have twice, these two numbers need to add up to 6, and you need to have twice as many 1 over x's as you have x squareds. So the only two numbers with that property are 4 and 2. So k should be equal to 4. But you can do it algebraically. I would just recommend doing it by like looking at it and thinking about what value of k would make all the x's cancel out. But if you want to do it algebraically, you could write 6 choose k times 2 to the 6 minus k times x to the 12 minus 2k. When I just raise a power to a power, I multiply the powers, right? I have 6 minus k copies of x squared. And then this one is interesting. I get minus 1 to the k times 1 over x to the k. Grouping all the numbers and the k's together, I find that this is equal to 6 choose k, 2 to the 6 minus k times minus 1 to the k. And now it's going to be x to the 12 minus 2k divided by x to the k. But this is the same thing as when you divide exponents, you just subtract. So this is really the same as 6 choose k, 2 to the 6 minus k. This is not the way I would recommend doing it. I just recommend doing it by inspection. This is x to the 12 minus 3k. And if you want to set this thing equal to 0, you can find k. So you can do 12 minus 3k equal to 0. So that tells us that k equals 4. And put that together, and you get that this coefficient, when you plug in, you get 6 choose 4 times 2 squared times negative 1 to the 4th. This would be like 6 choose 2, which is 15 times 4, so it would just be 60. And I'm not going to ask any like really complicated setup here that the algebraic way would be the best. I hopefully you can think of what weighting, what power of x squared and what power of 1 over x you would need to, just by looking at it, to decide what value of k you should put in. And also, one observation is like, you don't need to go through all of this. The only important thing is just to ignore all the constants at first. This makes it look really complicated. All you need to get to, the only part that I would say is important if you want to do it algebraically, is you need to just find k. So just focus on this expression. And then that would help you find k. Do you guys want to try a similar example to that one? Any questions? Any questions on this one? Okay, let me give you a similar example just to see how you do it. You don't have to write all this out. You could just say, okay, k, just look at it and tell me what k is, and then plug in and get the expansion. So let me give you another one. So try this one. And you can just leave it as a exponent and combination because I think the number is going to be a little bit big. You can leave it as the exponent and the combination. And message me when you got it, or if you want to, anyone volunteer how they thought about it. Also, you can message me if you're stuck, if you're not sure how to start it up. And I really don't recommend um, when you're first doing these. I don't recommend focusing, like trying to set it up with a formula and doing it the way that I showed you. That's like the rote way. It's a decent way to do it, but I recommend just trying to think about how the binomial pattern works, and maybe write down the general pattern if that helps. But then just think about, okay, try to guess and check essentially, because the one I'll give you will be pretty simple. And if you start writing down all the equations, it's just easy to get mixed up in the algebra, and it's like needlessly complicated. Try to guess and check, and try to decide, okay, I need to make sure I have a total, like whatever expansion whatever type of term you have, you're always going to have 8 factors. So you got to pick some amount of x cubed and some amount of negative 2x. How many of each do you pick so that the x cubes and the negative 2 over x, when you multiply them out, they're all gone? That's kind of the mindset that you should have. Once you figure that exact weighting, like, okay, I need like 5 x cubes and 3 negative 2x's, then you can just say, okay, that's 5 and 3. I know that's 8 choose 5 will be the coefficient, and then the other exponents I can find the constant. Let's see here. I don't actually, let me think about what the number is. The number here would be, we got a few good answers. And it's okay if you're stuck. These are a little bit more difficult. Good. It's good to do also make some observation. Let me see here. Anyone want to volunteer and share how they did it? Any of the people that I messaged?
I can.
Go for it, Alex.
If you write it, it's going to be way too shaky for anyone to understand if I try.
Yeah. I can write. Go ahead.
Well, I just looked at it and tried to just figure out what numbers would make the x have the same exponent. So I looked at the 3 and saw that it's going to be a smaller number than what the k would be. So because when you multiply any of the numbers by 8, it's automatically going to make it quite a bit bigger than it would be for the other x.
Mm-hmm.
2 times 3, that's 6, because 2 minus 8 is also 6.
Nice. Yeah. And one thing, one kind of simplification, if you don't want to deal with like the last thing the last problem, the way I did it there, you can just focus on the powers of x. So just like purely don't think about the -2 or anything in front of the x cubed. Just set it up and try to make sure that this is the exponent is this is x to the 0. Or just kind of look at it. I like, Alex, your idea that, okay, you're going to need to have way more, like maybe even thinking not as like, because it looks kind of confusing like this, maybe doing it like this and reminding yourself that a plus b is equal to 8. That might look a little bit better, actually. And then it's, okay, what quantity, what two numbers that add up to 8, but 3a and -b cancel out. So Alex, when you did that, what did you get for the exponents?
So a was 2 and b was 6.
Nice. So this might be actually the cleanest way, oops, sorry, the cleanest way to set it up, actually, now that I think about it.
So in this case, we're just going to cancel out, right? So it's 0 in total.
Exactly. You want to. That's right. A plus -b, and the reason you have -b is because it's 1 over x. So it's really like this is really the same as. Let me just move it over to the side. This is really the same, equivalent to x to the third 3a times x to the -b, which is equal to x to the 3a minus b. Okay. Awesome. So now once you have that a is equal to 2 and b is equal to 3, I think this might be a better, oh sorry, b is equal to 6, thank you. Where did you go from here?
Then if k is equal to b in this case,
Mhm.
I know it was going to be 8 over b, so I filled in the 6. So it was 8 choose 6. And then I just filled out, I guess, the equation like you normally would when you distribute the exponents.
Awesome. So x to the third to this, second power. And earlier I wrote 1 over x, just so that I didn't kind of, I'd focus on purely the powers of x. But now you have to remember that there's a -2 floating around there. So this to the 6th power. And you already know that all the x's will cancel because you're going to have x to the 6 in the numerator and x to the 6 in the denominator. And just double check that 2 plus 6, that you have 8 overall terms. And this looks really good. 8 times 6 is, 8 choose 6, sorry, is 8 times 7 over 2. So that's 28 times -2 to the 6, which is 28 times 64, and that comes out to 1792. All right. How did you guys feel about this one now that you did an example on your own? Hit yes if you feel a little bit better. Please hit no or message me if you're still like a little bit shaky on the idea. Okay, about half and half. So I guess one approach, I think that's a little bit, I think the last way I explained it was not very good because I had like k and then 8 minus k. I tried to do too many things at once. Maybe a better approach is to always think of binomial expansion. So let me see where I write that. You can always think of binomial expansion like, if I try to do it this way, x cubed minus 2 over x to the 8th power. The terms in the expansion will look like, the terms will appear like this. All the possibilities you can get for different values of a and b. So it'll be a choose a, x to the 3rd to the a, and then minus 2 over x to the b. So you have to find two weightings, two different powers, a and b, that add up to 8. And moreover, you want 3a minus b, because that's related to the exponent of x, you want that to be equal to 0. So this gives you a system of equations you can solve. So you definitely have a plus b equals 8. That's just because the overall exponent. That's this one. But then you have as well 3a minus b using the laws of exponent equals 0 because we want the constant term. And then you can solve, this is a pretty straightforward system, and you can solve for a and b, and you can plug back into the equation. So if you look back in the notes, you'll see it's exactly what I wrote before. The only difference is, like, I was using a, and instead of b, I was using 8 minus a. So that's made it look like a lot more confusing. So I think that's my fault for introducing that kind of confusing notation, but it's good to see both approaches. So please look back if you were confused and totally lost in how I did it the first time. Just look back and just see that I didn't do anything really that different. Just this is a cleaner way of looking at it. Okay, great. Are there any other questions? I saw there was a question on 39. And then I'd like to, if you guys have any questions about the test, I'd like to go over that also. So let's take a look at number 39. This was a term in the expansion of ma minus 4 to the 5th has a term minus 5760 a squared. What is m? Okay, so this one's a little bit nicer to set up. Can anyone offer their approach?
I can do it.
Go for it.
I started with like 5 choose 3 because that's the term in the that will get you the a to the 2nd power.
Awesome.
So I did 5 choose 3 and then m times a to the 2nd power and then -4 to the 3rd power. Yeah,
exactly.
like that. And then I just solved it and then I isolated m as like a variable on itself, and then
awesome.
I solved for it.
Great. Yeah, let's see. This is going to be m squared. 5 choose 3 is 10. And so this is 640, I believe. M a squared. And we want it to be equal to minus 5760 a squared.
I think it's
Oh.
negative 640 because it's negative 4 to the third power.
Perfect. Does that look good?
It's negative 640 because it's negative 4 to the third power, I think.
Gotcha. Okay, yeah, I just put the minus sign there on the side.
Oh, sorry, I didn't see that.
And then what do you get when you divide 5760 divided by 640? Is that
that gives me m squared equals to 9, and
awesome?
then m equals to 3.
Sweet. M squared is equal to 9, and then m. I technically could also be. Wait a second. A term in the expansion. Hang on. Oh, how do we get the negative 640? That was.
It's the 5 pick 3, which is 10 times negative 64, which is negative 4 to the third.
Nice. Yes, that's correct. Yeah, so Jeremy, that to get 640, this is, just to write out, this is 10 times m squared a squared times negative 64. So I jumped some steps there. This would be negative 640 m squared a squared. Very good. So one interesting thing here, though, is we found out that m squared is equal to 9. Why? That's interesting. Because the answer, they say m squared equals to 9. So you said m equals 3. Does anyone see why it can't be negative 3? I'm not sure I see why. I feel like 3 or negative 3 would work, unless I'm, wait a second, if it's negative 3. Hmm. 40. Yeah, I'm not sure for 39. Does anyone have the answer comes out to m equals 3, but I don't see why it can't be negative 3 either. And maybe they have oversight, or maybe I'm missing something, but I'm curious what you guys think. Why can't m be negative 3?
Maybe try plugging it back into the original equation.
Right. And if we do that, then, and you expand it out, you get, you'll still get, like, plugging in negative 3 right here, that makes it, that will make it overall, that will still make it, the overall expression, negative 5760 a squared. So I'm not sure why it can't be choice A for that one, but if any of you have another idea why it can't be choice A, or maybe they have a typo there, please let me know. But, okay, any questions on this one? All right. Thank you, An, for sharing your explanation. It was very good. Let's move on to the practice test and try to do a few of those. Do you guys have any questions from the practice test that you're interested in working on?
Could you go for 12? Oh, sorry.
Yeah, no problem. 12.
Over 12 first, yeah.
Oh, awesome.
And any, yeah, just throw them out. Any other ones? So 12 for sure.
Also do 8. Can we do 8 as well?
Of course.
All right, thank you.
Mm-hmm. And then, yeah, so 12 is very good. We talked about 12 a little bit in an earlier class. At a froyo place, they offer 4 toppings: sprinkles, Oreos, almonds, strawberry. How many ways are there to get toppings for your froyo? Kieran, do you remember a similar question from the homework?
I don't remember if it was in homework, but we definitely went over it where you could choose yes or no as an option for each choice.
Yes.
And I distinctly remember that, and that's why if you solve this in 2 ways, you get a bonus. And that shocked me. But then I tried using that way, and then I tried using the regular way, I thought, and I got marginally different answers, and I was really confused by that. So
is your margin just 1?
Yep.
Oh, okay. So I think, yeah, let's go through your 2 ways. That sounds, I think you got it. You just forgot one simple case. Okay. But one kind of case that's easy to forget about. So 4 toppings can pick any subset of the toppings for your ice cream. And the order doesn't matter. So we don't care if you put strawberries sprinkles on top or sprinkles on strawberries. It's going to be the same thing. Okay, so Kieran, what was the first way you thought of, what's the original way that might make sense?
So I thought that, the original way for me was there are 5 scenarios. So there's 4 toppings, 3 toppings, 2 toppings, 1 topping, 0 toppings.
All right, let me write here. Number of toppings. Number of ways to pick.
Yeah.
So 4, 3, 2, 1, 0. Okay, and what's underneath each of these?
I essentially had it for 4, it'd just be 4, choose 4.
Exactly, there's only one way to do it. Pick all of them. Then 4 choose 3 would be here, 4 choose 2, 4 choose 1, and 4 choose 0. That's perfect. And then what do these all add up to?
16, I believe.
Yes. Excellent. Okay. Does anyone have any questions about kind of how we thought about it here?
Why do you not do it with 5 instead of 4?
Well, I only have 4 toppings, so out of 4 friends, at most I can pick 4.
But so why do you do 4? Okay, wait, never mind. I get it.
Yeah, 4 choose 0 is important. That's the case where you actually just don't want, you get the ice cream and you're like, I don't want any toppings. And then, Kieran, what about the other way you thought about it?
Yeah, so that's where I was more confused. But I think Adam actually kind of pioneered this way, or at least for me, he did. But he just his idea was that for each topping you can choose yes or no.
Exactly. Yeah, so there's like, what is it? What are the toppings? Sprinkles, Oreos, almonds, and strawberries. If you do a tree, like you go up to sprinkles, you say yes, no. And then in those, that branches off your universe into two other universes. The one where you picked sprinkles and the one where you didn't. And now you have to, in each of those universes, you have to make another choice. And so forth. And at the very end, you're going to have a whole bunch of different toppings that you can pick, and you'll have overall 16 subsets. This is 2 to the 4th equals 16 subsets. This is all no's, so no, no, no is at the very bottom, and all of the toppings at the very top. Yes, if you're comfortable with this tree that we drew. Awesome. So both approaches are totally fine, and hopefully this can help you understand the bonus. That why are the sum of the nth row of Pascal's triangle equal to 2 to the n? It's exactly an example of that idea. Okay, so did that clear up number 12? Any questions still? I think a common thing with this one is to like be off by 1. Just remember that you want to include the case where you don't walk out with any topics. So that's the tricky thing. Okay, let's do number 8. There's definitely going to be one question about something about picking cards. So if you have a 5-card hand, is dealt from a deck from 52 cards. How many hands are the same suit? So there are 4 suits. There's the hearts, clubs, diamond, and the spade, I think. I'm sure that kind of looks like that. So, I'll do this one in red. Let's do it. So, anyone have any thoughts on this one?
It's set up like the queen problem of, I don't know.
Uh-huh. Go ahead.
Without having to worry about the rest of the deck, kind of.
Yeah. So what do you choose first? How did you break it up, Alex?
13, choose 5.
Nice. And where did you come up with 13? Why did you do that?
Because I know we're just looking at one suit at a time, and each suit has 10 cards plus 3 face cards, so 13.
Nice. So exactly. So 52 divided by 4. So choose 5. Choose 5 from 13 identical suits. 13 of the same suit. Okay. And then what do we need to do after that? What should we account for?
Do you do it for every suit?
Exactly. Just do it for every suit. So you can either think of like doing like, so first you pick hearts, do 13, choose 5. Then you do clubs, do 13, choose 5. So you're adding them 4 times. Or you just think, okay, first I pick the suit that I want. There's 4 choices. And then once the suit is picked, I have 13 cards that I can pick from. I got to pick 5 of them. So you can do it as 4 times 13, choose 5. This is the number of suits. Any questions about these? Any other questions that you guys want to see from the practice?
For question 3,
Yes.
do we use do we go like 8 choose 3 or is it 8 P3?
Yeah, this one you're just choosing. You don't care about how they're ordered because it just says you're just selecting the cards. It doesn't say you have to line them up or anything or arrange them.
So it's just 8 choose 3 and then 6 choose 4 and then multiply those two together?
Good, but this one has, because it has the word at least, at most, always be careful with that one because that could include multiple cases. So let me write out that one.
It doesn't have at least. That's the bonus part, I think.
No,
Oh, that's the bonus. Sorry. Yes.
Also for like number 1, I
Uh-huh.
think it's 4 to the power of 5. Do you want us to do 4 to the power of 5 or just leave it as?
Oh yeah,
Like,
yeah.
do you-
So for number 1, I'll say just leave it as an expression. Number 2, I'll ask you to simplify. Number 3, I might ask you to simplify that one, but not the bonus. Number 4, I think I'll just say leave it as an expression.
Are you
I'll
going to specify that?
Yes, I'll tell you which ones
Okay, cool.
we'll need to.
And for the write a simplified expression for number 2, it's n plus 5 times n plus 4, right? We don't
Correct.
expand that out or anything, right?
I mean, you'll get full credit if you don't, but yeah, I think it's nice to expand it.
Oh, so you want us to do n squared plus
Yes.
whatever?
Yeah,
Okay, cool.
just follow that one.
Is that more simple?
Yeah, I don't know. That's a moot point for sure. It's not. It's expanded. It's simple. It's not factored. I don't know if it's like, it's up to you if you want to consider. I don't know which form is simpler, factored form or standard form.
All right.
But yeah, either way is fine. I'm not going to really look for that one too carefully. So I think unless there's other questions, I do want to show you one cool thing that I addressed last time, which was to talk about the pattern in Pascal's triangle. And please, if you've done this test, if any volunteers want to leave some comments, actually just say okay, number 3 I got, you can write 8 choose something, and just share your idea with the rest of the class. That would be really helpful, and I think you guys would, other students would benefit from that as well. And you can also email me if you have any questions at all over the weekend. And number 11 is a good one that hopefully now that we went over the examples from the homework, you should be able to do that one. But I want to show you something before just the last few minutes of class. So did anyone think about why the pattern in Pascal's triangle? So we wrote this out. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Let's just do one more. 1, 5, 10, 10, 5. So did anyone think about why this pattern is true? Like, why should 6 plus 4 equal to 10? Anyone have any ideas? Because we know that the rows don't require that rule that the previous ones add up to the next one. They just come from straight up combinations. When we thought about it, we didn't need to use the previous information to get to the next one. So anyone think of a nice way to explain why should, I'm just going to write it in terms of combinations. So why is 6 plus 4 equal to 10? Or in other words, 6 comes from, why is 4 choose 2 plus 4 choose 3 equal to, what's it, 5, that would be 5 choose 3. Oh yes, Alice, if people want to stick around, I can definitely go over number 4 after. So the first is, can anyone think of a general pattern you can write down that involve like a general identity that involves combinations that you can write down?
For that, maybe n choose r plus n choose r plus 1.
Very good.
Equals n plus 1 r plus 1.
Nice, awesome. So this is a really nice identity that essentially gives you this beautiful result of Pascal's triangle that you can add the previous two to get to the next one. Now this looks a little bit abstract, and you could solve it by just doing a little bit of algebra. So one thing to try if you want, and you can send me if you do this, please send it to me because I'd love to see it. Try to just do this with algebra. So try using algebra. Because you remember that there's a simple way to express a combination as permutations, and permutations we saw, like in question 2, permutations are really nice. They can simplify sometimes really conveniently. But there's another way that doesn't involve algebra, but just sort of some intuition about what you're counting. So let's try a slightly different example with like bigger numbers, so that we're not focused on the exact numbers, but on generally what we're counting. Why would this be true? Why would 99 choose 7 plus 99 choose 8 equal to 100 choose 8? So I'm just writing it down. I don't even know what these numbers are, but I know that this is true. How do I know that? What's a reasonable, what's a simple way to explain without doing any calculation why I know that this formula is true? It's a similar argument, like it's on the level of the argument when we talked about like why is 100 choose 2 the same as 100 choose 98. You can come up with a very similar argument where you don't need to do any calculation. It's a very, very nice argument. Anyone have any ideas? How can I convince you that this is true without doing any calculation at all?
Is it at all related, and I don't know, but is this at all related to like the thing with the planes with like how like 4 choose 0 is the same as 4 choose 4 or that sort of thing, if that makes sense?
It's not really related to that specific property of combinations. Um, but it's like, you know how we were able to explain that intuitively without any equation or any math? Just like an argument about reasoning, like just using pure reasoning about what you're counting. Like when you choose 0, you're choosing 4 to not pick, for example, right? Like the complement, the number of sets that have a certain complement is equal to the number of sets that have another n minus that size. So there's another argument that you can make here. That's not exactly that one, but it's once you hear it, you'll be like, oh, that's obvious. Just think about, like, really think about 100 people, and you're picking 8 of them. Why should it be the same as the thing on the left?
I'm not sure if this is going to come out cohesively, but
What?
picking from an extra pool of people is the same as picking from one less person.
Yes?
Then I'm not sure if I can explain why that is, though.
Okay, you're like 99% of the way there. But
I have it in my head. It's just words.
Yes, yeah. Can you express that idea? But do you guys see Quentin's idea? That's the main thing. So
Is it just like by having an extra number like the 100, you've made it so that when you were to multiply it all together, you have the same amount as on the other side of the parenthesis?
yes, it could work out. Let me kind of give you a flavor of like what the argument looks like. So a lot of these arguments that have combination identities, they're called combinatorial identities. We count things in 2 different ways, and then we say, oh, but they're actually like each object that we counted corresponds to this object in a one-to-one way. So for example, when we did 100 choose 2 equals 100 choose 98, we said, oh, when you pick 2 people, that's actually the same as not picking these 98 people. So there's a group of 2 and a group of 98 that correspond to each other. And that's why 100 choose 2 is the same as 100 choose 98. So can you think of 2 different ways to go about picking 8 friends out of 100? And Quentin he's like right there. So if you could build on that idea. So what's one way you can do it? One way is just you have 100 people, you pick 8 of them. What's another way you can go and pick 8 people out of 100? No, picking 92.
You don't.
Yes, picking 92 out of 100 would also work. That is true, but that wouldn't help us with this identity. Kieran, what were you saying?
Nothing. It's silly.
No. I mean, Quentin is right there. So if it's based off of that,
Well, I mean, Quinton said this last time, but like not choosing 92.
okay, not just yeah. Okay, that would give you a different identity. But what about 99 people? What could you do? Why should it be equal to that expression on the left? So instead of going in and picking 8 people right away, what could I do instead? How could I think of that group of 8 people out of 100? All right. Unless there's any objections, do you guys want to hear the idea? Okay. So if there's 100 people, so let's say we have 100 people. One way to pick 8 friends out of 100 is to say, well, there's 2 things I can do. Let me assume that for whatever reason, Billy at the very end, my 100th friend, no way I'm going to pick him. Right? And I think this is where Quentin was headed. So if you don't pick Billy, and you're only picking out of your 99 other friends, there's going to be 99 choose 8 ways to pick 8 out of 99. Oh, see, I'm at the bottom here. Or instead, so these are cases, let me put it, let me write it maybe up here. This is Billy. So this is groups without Billy. And how can I count the number of groups that have Billy? The number of groups of 8 that have Billy. If Billy is required to be in the group, then that's just 99 choose 7. So groups without Billy and groups with Billy are 2 different types of groups, and every type of group either is with Billy or without Billy. So if I combine those together, I'll have all groups of 8.
How is 99 choose 7 groups without Billy?
Yeah, so Billy's required to be there, right? So I need to pick another 7 people out of the 99 people left over. That's what.
So
Yeah.
in this case, Billy, like where it's 99 choose 7, Billy's automatically always going to be there, right?
Exactly. That represents the groups with Billy. 99 choose 8 represents the groups without Billy. So altogether, that will give you all groups. I wrote this earlier in the notes, but believe it or not, this is really a consequence of is counting paths. So the number of ways to get to if you put this like a little lattice, and you can do only, what was it, like only move down the lattice, down the grid. The number of ways to get to 10, the only way to get to the number 10 is you have to come from 6, or you can come from 4. That kind of also captures the idea. But what we didn't get to cover, and I encourage you to do this, just to see another way of doing it, which is not as insightful. I really like combinatorial explanations because they give you a really strong intuition of how somebody would have thought of this identity or why it's true. But one thing that's fun that I recommend you try is you practice using algebra to verify this identity. Simplify the expression on the left, make sure it gives you the expression on the right. Okay, there was a question Alex asked about number, or somebody asked about number 4. Let me just do that one. And then if you have to go, you're welcome to. I know I'm going over time here. So let's see, whoops. Oh, and one last thing here, something to think about. And don't just look this up, think about it for a little while. Do you guys notice something really cool? Let me just see here. This is something really neat. What do you guys notice about these numbers? 1, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1? Anyone notice anything neat about those numbers?
Each row is double the last.
Not double. What is 11? What did this 1, 1 and 121 remind you of?
Oh, like 11 times 11.
Nice. And what's 121 times 11?
11 cubed.
That's 11 cubed. What about this one?
I'm gonna take a wild guess. 11 to the power 4.
Yes. And then it starts to break down. So one bonus question, and just think about it before you look up the answer, is why do the powers of 11 show up in Pascal's triangle? And you don't need to look anything up because you have all the main ideas to answer this. And I'll give you just one hint. Binomial theorem, I told you, is like a general thing with x plus y. So depending on what clever things you use for x plus y, you can get a bunch of neat identities. So you can plug in different things that if you want for x and y, and you can find some interesting identities. So you're allowed to plug in any x. Oh, that's the hint I'll give you. Yes, and quickly, yes, you're right. If you add them and offset them, you do get that pattern. Okay, let me go to number 4. How many arrangements are there that have beluga, so the letters are together, but not necessarily in that order? Let's see. So